So then I'll say good morning again. Good morning. Just for the record, everybody here is fully vaccinated and tested and is wearing a mask, just so that people that see that video don't get confused. Right now, I'm not wearing my mask because I'm speaking. I'm kind of excited today. We have Rodney Brooks here as our guest. And let me do the usual thing and give you some biographic facts about Rod. He started in Australia at Flinders University, then moved to Stanford, got his PhD there. Also became a faculty member, then moved to MIT, started CSAIL, the Computer Science and AI Lab, as a founding director, I think, right? And now he's Professor Emeritus at MIT, but he's also a serial entrepreneur. He started, I think, in the 80s with Lucid.
Yeah, Lucid. Yes,
Lucid, you've forgotten about that.
Well, I'm surprised you knew the name of it.
Yeah. And obviously started iRobot, a company worth $2.5 billion today. And most recently, Robust AI, which he's a founder of, and I think the CTO.
Yeah.
He obviously is in all the national academies of the US, of Australia, and has received, interestingly, the Computers and Thoughts Award from the AI community and the Technical Field Medal from the robotics community. This is kind of the Nobel Prize of robotics. So I think he has always solidly had his feet in AI and robotics, which I think is the right thing to do. He also kind of is a movie star. One of the movies is called Rodney's Robot Revolution, which, by the way, you can watch on YouTube. It's worth it. There's also one that's called Fast, Cheap, and Out of Control, which has a Rotten Tomato rating of 91%. So I recommend that. And then there's another one called, I think, Love Machine. I made the mistake of Googling that.
That was bizarre.
Don't do that.
That was bizarre. I didn't know what was coming.
Yeah, and today he's going to talk about, is cognition computational? And this has already caused quite a controversy yesterday when we were discussing, because everybody is like, of course it's going to, what else could it be? But let me warn you, this is a trick that Rod has pulled off several times in the robotics community, that he said something that went against the grain of what everybody thought to be true, and he was right. So today, I think you're going to ask that question to all of us, and I hope you will accept the challenge and we'll have a very vivid discussion in the past. But I can only say that from my personal perspective, we're going to listen today to somebody who has really shaped robotics as a field, and certainly the lab in the research in my lab, and also many of the principal ideas that form the basis of our research center, Science of Intelligence. So it is with extreme pleasure that I welcome Rod Brooks, and I'm looking forward to your presentation.
Okay, thank you. Well, thank you all for coming here today to listen to this. This is the first time I've given this talk. It's not well rehearsed. I may get stuck in places because I haven't actually given the talk before. And I want to say it is a question here. I'm not saying cognition is not computational. I don't think it is. But I'm asking the question, is cognition computational? So last weekend, I went for a walk with my grandson, and I saw this side of the road. And you see on the left of the white line is where the cars go, and on the right is just this little verge where the cars don't go. And notice it's covered in stones and sticks and all sorts of things there, where the cars don't go. But where the cars go, the road is clear. So did the stones and sticks and leaves compute where they should go in order to leave the road clear? Would anyone think that was a computational thing they did in order to do it? I don't think the passing cars engaged in computation about where they were going to send the sticks. We would explain this in some other way, that the cars go, they randomly scatter the things, and they keep randomly scattering the stones and sticks until they're in a place where cars don't hit them anymore. And that's how this came. And you could probably, if you're a deep learning guy, you could write a, minimization with an argmin or something in big equation, but I don't think that's a good explanatory way of talking about this as computation. Here's a Falcon 9 carrying 2 astronauts to space last year. Why does Elon Musk bother to build rockets in order to get things into space? Why does he build a rocket? Why not just write a computer program? You could write a computer program. You could write a computer program, a big one that uses lots of processors in the cloud that have a bigger carbon footprint than the rocket. You could do that. But that's not how he gets to space. So, because I think we probably agree, getting to space is not a computational problem. There's lots of computers in simulations, there's lots of computers controlling it, but it's not just code that gets things up into space. It's not computational. There's something else going on. It's physics. So you could have a computational simulation of the rocket, which is very accurate. You could have lots and lots of computation, but that simulation in computation wouldn't get things into space. What about these things? There's a mouse brain, a macaque brain, a chimpanzee brain, a human brain. Here's my question. Are these computers? And sort of the popular way of thinking is, yeah, they're computers. We have a computer in our head. Sticks and stones on the side of the road, probably not computational. Rockets, they're not computational, but somehow these are computational. And the question is computation what they do, actually? Are we right about that? Why do we believe that they're computational? Is thinking or even just controlling a creature that exists in the world, is that a computational problem? Is a jellyfish doing computation? What about a tree? We know from recent work, just in the last few decades, that plants and trees, can search for food. They do it very slowly, so we don't see it on our human timescale. But they search, they recognize kin, they provide nutrients to their genetic relatives. They don't have, as far as we know, neurons. They don't have electrical signals going along virtual wires, as we think of the axons and dendrites of neurons. So they don't seem electrical in how they do this, but they do these behaviors in some way. Are they computational if they don't have wires and electricity? Or are these things something else? And that's the question. Have we decided that computation is what is in our heads, and that's what we just assume, or are we perhaps wrong? And even if you could do, like for a rocket, for a SpaceX rocket, you can do a detailed computational simulation, but you still don't get things into space. Here's the question. If these are not fundamentally computational, can we build intelligent AI programs using conventional computers? Or is there something else that we need to be using? Many people, and also on the committee that is visiting, although she's not here, Patricia Churchland and Terry Sinofsky, this is their book that's the 25th anniversary edition of their book, so it was in the 90s, talked about the computational brain. And there they say, well, you don't have to worry exactly what computation is, because it's what the brain does. So that's the definition. But I'm wary of that, because if you change the definition of computation to be what the brain does, now you lose being able to answer the question, if the brain does that thing, and it's different from what our computers are, can we write a computer program that's ultimately going to be intelligent or not? We don't know if it's a different thing. So I object to just saying computation is whatever the brain happens to do, because there's actually a tremendously large field of computer science about what can be computed with our computers that we build. And if they're different species, different sorts of things, maybe we're ultimately not going to get to where people believe we will get to, building intelligent programs. And we know we've had, incredible computational resources thrown at the weather, and we still can't predict the weather. So can we do anything about thinking or intelligence? So computation itself is actually a socially constructed thing. And I'll talk about how it got socially constructed. mass seems to be a fundamental property of the universe. Energy, fundamental property of the universe. But what we call computation was something that was constructed by people and agreed upon in a very funny way, and I'll go through that history of what it is. It roughly describes what we call computers, the official, Turing definition of computation, which everyone ultimately refers to in theoretical computer science classes. This is roughly what our computers do, but I'll talk about that too, because it's a bit fuzzy the way people throw, even within computer science, people throw computational and there's something computable around with abandon in ways which is not very accurate. I think many things in our world are not fundamentally computational, like rockets. They're not fundamentally computational. Computation can be used as a metaphor, and we use computation as a metaphor for lots of things. And it can be used to do simulations, but simulations only simulate some aspects of any phenomenon. They don't capture everything. And here's my point. If we say that computation is anything we want to call computation, it can be anything, then we certainly lose connections to our devices. And we don't even know whether we can have an artificial jellyfish run by a computer that's as good as a real jellyfish. We don't know that. So back in 1956, when the famous AI conference was held, this is the first part of the proposal, first paragraph. There were 4 authors attached to it, but it was really written by John McCarthy in 1955 for the 1956 thing. And he first used the words artificial intelligence. The first time that appeared anywhere was there. And he doesn't explain what it is. He just says artificial intelligence. People thought he maybe should have said cybernetics, but he really hated Norbert Wiener, and he didn't want to call it that. Everyone who met Norbert Wiener thought he was a terrible bore, and they just wanted to distance themselves from him. And he says, the study, second sentence, the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So he says any aspect of intelligence can be simulated by a machine. That's his second sentence. Second paragraph, if a machine can do a job, then an automatic calculator, he meant what we call computers today, can be programmed to simulate the machine. So he was making an argument that the automatic calculators of 1955 were universal machines that could simulate any other sort of machine. But how did that belief come about? And I've been questioning this for a long time. I've been a grumpy old guy for decades. So this is a paper I had in Nature back in 2001 about the relationship between matter and life. And there I said that maybe we need something more than computation. And maybe it's not particularly threatening. Maybe it's not weird like quantum computers, because that was all the rage in 2001. Oh, it's still all the rage, isn't it? Yeah, they're about to come. Anyway, maybe it's not a threatening notion. Maybe it's as non-threatening as computation was threatening, but maybe we don't have all the tools that we need to do intelligent machines. And even Oliver just mentioned that I won the Computers and Thought Award back in 1991, and 2 things about that. I was surprised that I got that award, totally surprised. And after I got the award, they changed the rules so that someone of my age could never get the award again. So I just snuck in there. But they also said that I could have a paper in the proceedings where there was a page limit of 5 pages, but I had no limit. They thought maybe I'd write 7 pages. I wrote 27 pages. And it was about maybe getting to intelligence can be gotten a different way. And I talked about situatedness. I've just cut out some pieces, that a robot in the world doesn't deal with abstract descriptions, but it's the here and now of the world. It's embodied, so what it does in the world changes what it's going to compute because it changes its perceptions. And the intelligence on the right there is not limited just to the computational engine, I said at the time. It also comes from its situation in the world, the signal transformations within the senses, and the physical coupling of the robot with the world. And since I've been here since yesterday morning, I've seen a whole bunch of projects that aren't quite connected to this view. So that's why I felt like this is the audience to try this talk out on. I also talked about cybernetics in that paper, and these are some paragraphs in order, and I've underlined the important stuff. Cybernetics was another tradition which got beaten by computationalism in the 1950s. Up until that point, they were neck and neck on which was going to win. Cybernetics did not win. Although the Australian National University has a new department of cybernetics, which is quite surprising. But cybernetics was dealt with in terms of all possible behaviors of an individual machine. They tried to characterize all the behaviors, whereas artificial intelligence tries to have a behavior or a intelligent program. Down in the green there, it was in the realm of continuous functions. Cybernetics assumed that functions were continuous and mostly differentiable almost everywhere. When we're talking about computational models, we don't make that requirement. It's much more discrete. It also said, in the orange top, there was less of a notion of representation as an abstract, manipulable entity that artificial intelligence had. So one of the things artificial intelligence did was use representations, explicit representations. A lot of the work in red there was that it was, trying to understand how animals change their behavior through learning, and that led to better adaptation to the environment. So it was very much coupling of the creature to the environment, which artificial intelligence largely threw away. So I've been, going on about this for a while, but this is the rest of the talk computation is socially constructed. People throw around known results about computation to make all sorts of arguments, and often they're very imprecise arguments. But if you're talking about computation, then somehow it's precise. But in reality, it's not. And there were four fields: artificial intelligence, artificial life, neuroscience, and abiogenesis. 2 engineering, 2 science. Abiogenesis is how life comes from non-living matter. Those 4 disciplines all arose in their modern form in the period 1945 to 1965, and it was all the same people who were doing those 4 fields all at once, and I'll show that. And those first 3 of those fields, AI, A-Life, and neuroscience, have said that they're about computation. So maybe that stops us from having grander thoughts about what it might really be. So the history of computation. We've had arithmetic for a long, long time as human beings. We've had algorithms for at least 2,000 years. So Herons Method, which computes the square root of a number, is one of the earliest algorithms. You guess at what the square root is, divide it into the number, and then take the average of that result with your guess. You get a better guess, and as you keep doing that and iterating, you get more and more precise. And people sort of think of it as it gives more digits with more iterations, but you actually don't quite have the digits unless you redo the arithmetic every time. So those algorithms are often practical, inspired by land adjudication. That was a big reason for trying to figure out the area of, if you got the square root, then you could figure out what the area of a triangular piece of land had. Oh, there's a whole crowd out there. Yeah, no, they're really angry. Look at this thing. Yeah, no. And so algorithms are something we think about in terms of writing down numbers and deriving new numbers from those we've already written down. And this became industrialized in around 1614. On the left there is John Napier, who lived in Edinburgh, and he spent 20 years computing some tables. I'll show you those tables by hand. And then Kepler used those tables for his annual ephemeris that he did. And what was the ephemeris? It was where all the planets would be over time. So it was a tool for astrologers. That was applied astronomy. And he was so pleased with these new tables because it made his computations that he was doing by hand so much easier. And in his 1620 ephemeris, in the middle there, he has this whole preface just glowingly talking about how John Napier has changed his life for the better. It's all in Latin. So in 1614, John Napier published this set of tables, and there were logarithms of sines and cosines over a 90-degree interval. He spent 20 years computing by hand. There were 2,700 lines in the table, 10,800 computed numbers, but he made a mistake early in that 20 years, and the 7th decimal places are all wrong, but it was still an improvement. Logarithms of sines and cosines. He actually invented logarithms, but he didn't understand them in the modern way we do. He knew that if you added them and then took the anti-logarithm, you got a multiplication, but he didn't have a good, solid mathematical argument for how they worked. But they were good for other computations. So this was the first table of numbers. And then as the Industrial Revolution came, everyone had wanted tables of numbers for all sorts of things. When Taylor's theorem came about in 1708, that you could decompose any function into, using its derivatives, into something that you could compute the values of the function, it turned out there was an easy method called a method of differences where you just did lots of additions and you could compute these tables. And by 1760, there was such a demand for tables of all sorts of functions that people were trying to mechanize it. Leibniz tried to build some machines to do it. He wasn't successful. But then Charles Babbage in 1837 talked about his calculating engine, which he never built because he got a better idea, which was the analytical engine. And so he didn't build the calculating engine. But the calculating engine was to use the method of differences and even output directly the typeset printing table, so there was no human in the loop because they knew that humans were fallible by that point, and so trying to produce these tables. So he came up with a better idea. So this is a replica that was built at the London Museum of Science about 25 years ago, but there are other replicas. You can find videos of them. There's ones made of Lego that actually work, so there's infinite fun that can be had. But he came up with the analytic engine instead. And the analytic engine we mostly know about by a translation that Ada Lovelace did of an Italian scientist who described what the analytic engine was going to be, and he wrote about it in Italian. There's no original writing really from Babbage. Ada Lovelace translated it from Italian and then put more footnotes than the original description and described it in much better detail. She did point out that it could do more than just arithmetic, but it had a central mill which could do addition, multiplication, division mechanically. It was going to have it. We call that an arithmetic logic unit today. Had a sequencer based on punch cards for a program with loops possible, except they never quite figured out all the details of how the loops were going to work. There were punch cards to make to run weaving machines to make patterns, but they didn't have loops. They were just, every line of the pattern of colors was sequential. So the idea was that there was going to be loops. There would be a store where you could have variables, many variables, get them into the mill, do an addition or subtraction or whatever, multiplication, put it back. So it was like a modern computer, and with input and output facilities. And Ada Lovelace had the first program. This was to compute Bernoulli numbers, and she also invented the first bug, because that particular statement has the arguments to division switched, but she never got to run it, so she never got to try it out. And it's not really a program so much as that she wrote here. It's a trace of what the statements would be like if they were executed in the right sequence. And she talked about loops, but she didn't actually represent the loops. She just unwound the program. But still, she invented a lot of stuff. Now we jump to Alan Turing, 1936, on computable numbers with an application to, however you say that word. Yeah, and I don't know. It just suddenly occurred to me. For someone who's not a computer scientist, does that have a meaning? And what does it mean? A decision problem. Well, that's what it was. Okay, I never knew it was. And so Hilbert, people still go after the original Hilbert problems, so 23 or 24 of them. But he then had an extra 3 problems, a new set of Hilbert problems. And solving a Hilbert problem has always been the way to become a very famous mathematician. So Turing was this young kid. He just got his undergraduate degree from Cambridge, and he heard about these Hilbert problems, and man, he wanted to do one of them and be famous. And the way to do them was to disprove them. That was the quickest way. To actually solve them was really hard if they were true, because they were hypotheses. Hilbert's problems, he didn't know the answers. He really wanted to put them out there. And Turing's professor, Max Newman at Cambridge, had rephrased in a class. Hilbert's language was that there was a definite method to solve problems in arithmetic, in a sense. And Max Newman talked about it as a mechanical process. So that was what was in Turing's mind, a mechanical process to decide whether a mathematical assertion is true or not. Decide. So his famous paper, if you actually read it, first he had to hypothesize something that he could argue was the most general mechanical process. He spent 29 pages on that. And then he had to prove that that couldn't be used to decide these theorems about arithmetic. So that was just 4 pages. So he was in this position where he had to have something that was a machine that could do stuff, but then he wanted it not to be powerful enough to do what Hilbert had hypothesized. So he's had a bit of a conflict of interest there in this. He wasn't out to invent computation in this paper. He was out to disprove this hypothesis of Hilbert. And Kurt Gödel had already disproved the 2 other problems about consistency and completeness, and Turing was trying to disprove the decidability problem. And the way he talked about what computation would be was he modeled human computers. Well, what's a human computer? And he didn't have very good arguments about this, and we'll see that in a minute. So it was a sort of trashy paper in a way, but it did lead to a few things that we still remember. So he did pretty damn well, and he's on the 50-pound note in the UK now. But he modeled it after human computers. What were human computers? See that says the computing division and the computing section on the left there? There's a whole bunch of women. Oh, they're not all women. There's the supervisor, that's a man, and there's one guy in the middle. Everyone else, and they're following instructions on how to compute the numbers for those tables, because they still didn't have a mechanical way of doing it. So computers were humans who cranked out tables, just like those of Napier and the things that Babbage had wanted to do with his difference engine. And Von Neumann, when he was designing the EDVAC computer, which we call the computer now, it wasn't called a computer, it was a calculating engine. In his design document, he says, it's really just a computer, but he meant a human computer is following instructions, doing arithmetic by hand. They weren't called computers till later, the devices. Computers were people. So this is from Turing's paper, and he's trying to say, well, this thing I described that can do calculations, why has it got a finite memory? Well, because humans have finite memory. So that's for those who know Turing machines, for the set of rules that it had is finite. There's a tape which is infinite. And he said, the rules are finite because humans are computers and they have a finite memory, so the rules must be finite. And then he had the infinite tape as a model of someone having an arbitrary amount of paper that they could use. There was no limit on the amount of paper that was no artificial limit. And he said, in the second paragraph that I've got there, no attempt has yet been made to show that the computable numbers, his definition of computable, include all the numbers which would naturally be regarded as computable. So he wasn't sure that he'd really got it. He said, fundamentally, I'm going to appeal to intuition to show that I've got these machines that can do everything. So he used intuition. And there's a whole set of 9 different intuitive reasons he gives. Well, it seems like it can compute a lot of numbers, but it's very intuitive. But that didn't stop there. People struggled with whether his definition was all that there was for computing. But eventually they got to a point, why worry, be happy, seems like it's okay. It's never been proved, and there's the Church-Turing thesis, which is about whether it is, and quantum computers say, no, it's not what there is. But Moore's law happened, and we've just had incredible power from what we call computation. It's transformed our world in so many ways. But is that all a machine can do? Does it capture everything? Minskys 1967 book, it's a beautiful, beautiful book on a theoretical book on theoretical computer science, computation, finite and infinite machines. He talked about whether Turing was right or not, and he said, and this was so Marvin, the reader who finds himself in strong disagreement, either intellectually or more likely emotional with what I'm about to say, you can still appreciate the beauty of the theorems, even if you don't like me saying that, yeah, what Turing said about computers is probably right. He said the abstract idea of a machine is a specification of how a physical machine ought to work. And then he talked about it in terms of gears made of metal or wood, and just as long as they're able to preserve certain aspects of their form to a sufficient degree, then that's all you need to compute stuff. And there's an implicit assumption here, which is not true of biological systems, that in digital computation, if you do the same computation twice, you get the same answer. And that is not true of so many other systems, including our wet. So he says, any process which could naturally be called an effective procedure can be realized by a Turing machine. They didn't have a good argument. And he sort of admitted it, because he said, you might get angry at me. It was intuition. Donald Knuth, very famously, his first 3 volumes on fundamental algorithms, he says in the first few paragraphs, he used Euclid's algorithm as to get the greatest common divisor of 2 integers as an example of what an algorithm is. He referred to a very obscure Russian mathematician, but he said algorithms have to have finiteness, definiteness, that's do the same computation twice, get the same answer. Input, output, and they must be effective. And what did he mean by effective? He defined effectiveness as the operations to be performed in the algorithm must be sufficiently base, simple, that they can in principle be done exactly and in a finite length of time by a man using pencil and paper. Man using pencil and paper. Although he did quote Ada Lovelace right at the start of the chapter. So he says that an algorithm is something where you can do each step with a pencil and paper in a finite amount of time. And as a counterexample, he said if the step relied on whether Fermat's last theorem is true or not, that wouldn't be effective, because the proof or disproof of Fermat's last theorem wasn't known at the time. That would not be an effective step. So if a person can do it with pencil and paper, that's what computation is. And then he says, effective and experienced, so it's also powerful enough to do anything that we can do by hand. So it's intuitive, that's what he said, but he used intuition. Hopcroft and Ullman, 1969, they're still trying to think, are Turing machines really it? You know, now computers were a big thing. But is a Turing machine the definition of computation? Is that what all that machines can do? We're somewhat vague in our definition of a procedure. You know, they couldn't actually, no one's come up with good arguments. And he says, the strengths, they go on and they talk about it. This strengthens our belief that the Turing machine is general enough to encompass the intuitive notion of a procedure. So still, they weren't sure that the computation, which is Turing computation, is the basis of all computer science still. They weren't sure that was really a description of what could be done by machines or not. So, but by 1974, A.O. Hopcroft and Ullman, their famous book on design analysis of computer algorithms. Just 5 years later, Hopcroft and Neumann were two of the authors of the previous thing. They didn't even bother to ask whether Turing machines were it. It was sort of everyone had given up by then and said, yeah, that's it. It's fine. That's what machines can do, what Turing machines can do. But they did introduce their RAM model, random access memory, which is a finite amount of memory instead of an infinite tape. And they did talk about whether that equivalence was dangerous or not with Turing machines. And mostly that's sort of ignored these days, that our machines actually only have a finite working memory besides a finite program memory. So this is what we call computation. But, you know, I think why we like this version of computation is it's easy for us to talk about. And Barbara Taversky, I'm not sure that's how you pronounce her last name, her laws of cognition, she was at Stanford for her career. There are no benefits without costs. Action models perception, feelings come first. This is about human psychology. But spatial thinking is the foundation of abstract thought, number 6. And number 9, we organize stuff in the world the way we organize stuff in the mind. So we have this spatial understanding of the world. And we like to think about things in spatial terms. And we give explanations of natural phenomena in spatial terms. And you know, the RAM model of Aho, Hopcroft, and Neumann was, you know, there's a set of cells and you put numbers in them and, you know, they're memory locations in a computer and they stay there until you change them. You know, it's like physical caching when you're, you know, collecting nuts and you're keeping them for later. Birds can do that. So our hunter-gatherer thinking about place and relationships, you know, is now, from neuroscience, assumed to reuse our place cells in our hippocampus and our grid cells in our entorhinal cortex for abstract reasoning. So we use that machinery, which was for representing space, to reason about stuff. And we're good at that. We're good at that sort of spatial reasoning, but that's not everything we need for all sorts of explanations. So computation was agreed upon socially. There's a tremendous amount of theory which is followed, but there's some shortcuts about finiteness and infiniteness, and then there's lots of saying, this machine can do Turing computation, and they show how to represent the problem so that it can do it, but that change in representation is something that a person has to do. It's not automatic, so there's a lot of intuition goes into that. Computation, something that we can easily think about and reason about, and then these 4 disciplines, if you have this 2x2 matrix of science and engineering versus thinking and being, neuroscience, artificial intelligence, artificial life, and abiogenesis. Although when I did talk about this idea to a origins of life scientist recently, she got very upset with me using the word abiogenesis. She said, that's such an old-fashioned word. You shouldn't use that word. So I've made a mistake, but I don't have a better word for it. But these disciplines were all formed in the period 1945 to 1965, and there were lots of people that worked in more than one discipline. I haven't got anyone who worked in artificial intelligence and abiogenesis, but all the other pairs, I can point to individual people who worked in either 2 or 3 of these disciplines. And computation has become the primary metaphor or analogy for 3 of those 4 disciplines. It's not the primary metaphor for abiogenesis. That's all about chemistry still. So I'm sort of astounded by some things. Turing's definition of computers, when I finally read it, wait, computers are people? You know, I'd grown up, computers were machines, but computers were originally people. And then, rise of computational neuroscience, wait, people are computers? There's a little circularity going on here. Computation is all about what a person can do writing down numbers on paper, but that's okay, that's what you like. So there were 2 important precursors to that 20-year period, 1945 to 1965. Claude Shannon, who was one of the co-authors of the artificial intelligence proposal in 1956, he had shown that Boolean algebra could be used to describe relay and switching circuits. and he invented AND gates, OR gates, and NOT gates. Someone had to invent those things. We sort of think that's fundamental, but someone had to invent it. Before his 1937 master's thesis, people drew circuit diagrams of relays, but they didn't have a way of thinking about them abstractly. He showed that Boolean algebra could be used to think about them. If you read that paper, it's easy to find that master's thesis. If you read the paper, it sort of reads weirdly because he used a negative form of logic. So the plus and the dot are different, sound different than what we're thinking about, but if you transform them to negative logic, it all works. And then in 1943, this very influential paper by McCulloch and Pitts. McCulloch was the professor, Pitts was a young student in Chicago. They both later moved to MIT. They had this paper, A Logical Calculus of the Ideas Immanent in Nervous Activities. And they just made shit up. I'm sorry. They just said, McCulloch says we want to be as principled as Whitehead and Russell with the Principia Mathematica. We're going to have a logic to describe the brain. It's going to be based on Shannon's work of AND gates and NOT gates and OR gates. And, they describe neurons as two input machines with, if they're both excitatory, there were AND gates, with inhibition and excitation. They showed how you can make AND gates and OR gates. And they said, that's what the brain is, this bunch of AND gates and OR gates. And it was really influential. Newman Von Neumann, in his design of the EDVAC, he talked about not gates, but nerve cells. That was how he described the computer. And he used McCulloch and Pitts. Minsky, in his 1954 PhD thesis, used McCulloch and Pitts. Tremendously influential, and it was just not true in any shape or form. But McCulloch got to be a big deal. So von Neumann, I'll just show you how these fields would intertwine. Von Neumann came up with a description which he talked about in terms of organs and very much related to animals, of a self-reproducing machine in a 29-state cellular automaton. And he beat Crick and Watson to the central dogma of biogenesis, that there is a linear tape that is both copied and interpreted, which is what Crick and Watson showed. Yes, the DNA can be copied and interpreted, two mechanisms, although they didn't have the interpretation mechanism. That came a few years later after their paper. So, there's artificial life and real life. John Holland, who was a student of von Neumann's, developed genetic algorithms, which is the basis of artificial life, and has come back in popularity recently. Open Mind in London has suddenly rediscovered them after 30 years of them going away. And Holland was invited to McCarthy and Shannon's thing in Dartmouth. Unless you're an artificial life aficionado, you don't need to care about the last two things, but they were big events in my life when I was a teenager. But Warren McCulloch went to MIT, and his unscientific paper with Pitts inspired others, such as Marvin Minsky, to just make stuff up about the brain. His famous K-lines paper. There's no evidence that brains have K-lines, but he just talked about it, and it became celebrated in the artificial intelligence community. This is how brains work. He just made it up. McCulloch was also a co-author with Letvin and Maturana, and they wrote the first paper on functional neuroscience, what the frog's eye tells the frog's brain. And lots of people talk about what that paper says. I recommend reading it before you say what it says, because it's less obvious than lots of people. But it related neural structure to the behavior of a creature, the frog, for the first time. It actually showed how the relationship, they recorded from cells, they had animals, they did what, became a common way of working in neuroscience. That was real science that they did. And he had an intellectual posse who influenced everything across the Macy conferences, where there were people like Margaret Mead and anthropologists, sociologists, they went there and bulldozed in their view of reductionist science, whereas the other scientists were trying to be much more cohesive about how everything came together and what we would call situatedness and embodiment. And they got rid of that, his posse. And his posse included Pitts, Marvin Minsky, Stuart Kaufman, who went on to do the autocatalytic stuff to show how biological systems could generate themselves. John McCarthy was in the posse. Latvan, Humberto Maturana was one of them. Michael Arbib, some people may know Arbib very well. You were at he'd left UMass Amherst, gone to USC by the time you were there, but very famous guy. Varela, a student of Maturana's, was one of them. Manuel Blum, who's a very famous theoretical computer scientist, many others. And Wiener and McCulloch were both at MIT. Wiener and McCulloch did not get along at all, and McCulloch's posse sort of pushed Wiener aside and pushed out cybernetics. But this group were the arguers for computation as a primary metaphor for artificial intelligence and neuroscience. This is what I sort of said earlier. Sorry, as I said, this is the first time I've given this talk, so it's a bit not quite as smooth as it might be. People bandy around equivalences of computation, this system can do Turing computation, this system can do Turing computation, as a proof of universality. And then crazy people like Wolfram say, oh, that's what the universe is made of, Turing machines. It's all computation. But in the great McCulloch tradition, just make stuff up. It's okay. But we use computation it started out as a metaphor for what the brain might be and for what neuroscience might be. But it has now become what it is, with the computational brain from Churchill and Sinofsky. But when metaphors break, we get into real trouble. And we've seen breaking metaphors. Sometimes it takes centuries to fix things. My favorite example of this is phlogiston theory. Phlogiston theory of burning was that there was something common, a common material in everything that could burn. And that was held true for well over 100 years, even though the data did not quite match that. And it was Lavoisier in Paris, and who lost his head in the French Revolution, unfortunately, and I forget the name of the guy, the British guy. They showed that no, it wasn't, the common material wasn't in the thing that burnt, the common material was in the air, oxygen, which was what was involved in everything burning. So that metaphor of there being a stuff that is the burning stuff instead of the thing that causes burning completely screwed up chemistry for a long time. It took over 100 years to get out of, even though the data was there. We see this in quantum mechanics. Okay, I'm going to be snarky, so I put a tag there. Hunter-gatherers know about particles and waves, so it's got to be one of them. Is it waves? Is it particles? And this is the common thing in common descriptions of quantum mechanics. Well, we'll use this metaphor. No, that metaphor doesn't work for the two-hole double slit experiment, so we're going to use this other metaphor. Real quantum mechanicians, use an abstract sort of algebra which describes it precisely without relying on this intuitive model. And all the interpretations, the Copenhagen interpretation of quantum mechanics, the many worlds interpretation of quantum mechanics, are interpretations. They're not saying the underlying thing is different. They're just what's the metaphor we use. People want metaphors. Cosmology. There's too much gravity out there, so there must be more mass or matter than we thought. We can't see it, so it must be dark. So there's dark matter out there. And 95% of the universe is dark matter. But that's just a metaphor people are using. And hasn't been found. This may take a long time to fix also. So as fields, or as we mature, we invent new tools to get around inadequate metaphors and analogies. And I call these Newtonian black boxes. You might want to call them Leibniz black boxes, but So we appeal to them whenever minimal conditions of applicability apply. And what are they? Calculus is one of them. We just use calculus. We know when it's applicable. We have some preconditions, and then we can immediately get to answers. And it's sort of this black box, toolkit that we know how to use. Probability theory, Bayesian inference, group theory, numerical methods. All these are black boxes that we use. There's a whole theory underlying them. They're proved, they're thought about deeply, and then they're a tool that we just get to use. And they make certain assumptions about the world. And sometimes we gloss over details that turn out to be important when we are using these tools. You can get into great trouble if functions turn out not to be continuous and you're differentiating them everywhere. If you try to apply it when it's not valid to apply it, for instance. So we come up with new black boxes to plug the holes. So I'm skeptical that in the long term, 300 years say, we will still think of brains as computational engines. I don't think we think of trees as computational engines yet, even though they perform many behaviors similar to what animals perform. So maybe we need some more black boxes, tools to figure stuff out. And maybe it's going to take those black boxes to come. What would those black boxes be? It turns out I don't know. Who could have guessed? I don't know what they might be. I'm questioning whether we might need them, however. And there's been a couple of existing other approaches from the United Kingdom, especially Cybernetics talked about homeostasis, which is about self-regulating systems, an ability of a system to keep certain parameters within prescribed ranges. So that was used to talk about how animals maintain themselves. Grey Walter built his little cybernetic robots, which had goal-seeking homeostasis and learning with just 2 vacuum tubes to run them, but they were very nonlinear vacuum tubes. And then this other thing, which is a really hard one to understand, Maturana, who was an author of that Frog's Eye, Frog's Brain paper, and his student Varela, they were both from Chile, came up with autopoiesis as a way to describe, what's a cell? Well, any particular cell, over time, the atoms in there may change. So it's not the identity of the atoms are not important, it's the identity of the network of processes which maintain the metabolism of that cell over time. So, and they're continuously regenerating the cell. And this is very different from, say, a manufacturing thing. A factory that makes cars is a factory, and stuff comes in and cars come out. But in autopoiesis, it's the thing that is doing the manufacturing is the thing that is being built continuously all the time. It's really hard to read their papers. It just hurts your brain. But maybe in Spanish they're easy, I don't know, but in English they're really hard. So, people have tried to come up with ideas, and some of them may be right, about different ways of describing natural systems and talking about what artificial intelligence and robots could be. And I'm going to give 2 examples. I think, how much more time should I go for? It's 11:58. Because we started a bit late, right? Yeah. Okay, I'm going to give 2 examples where the structure, even a little bit of structure, complex things emerge, and it's really hard for us to think about them. First is something called Parondo's paradox. He's an I think he's an Argentinian mathematician. And the point is we have no good Newtonian black boxes to help us understand these 2 examples I'm about to give. Computation doesn't help particularly. So Parondo's paradox, we've got 2 random games. You either play machine A or you play machine B. You start with $50. On each play, you pull the handle of the machine you're playing with, and you either win $1 or lose $1. When you get down to 0 or you get up to 100, you walk out of the casino, okay? And there's these 2 different machines. Machine A has a probability of losing of 0.505 and a probability of winning of 0.495, and it's just a random number, and with win or lose according to those probabilities. That's a losing machine. If you keep playing that, you're going to lose on average. Machine B it refers to how much money you currently have. So it's got a little bit of structure hidden in here. And if the amount of money you have right now, you started with $50, if the amount of money you have right now, the probability of losing goes up to over 9/10. But if you've got something that's not a multiple of 3, the probability of winning is 0.745. Okay. Run 300,000 trials of this. Why 300,000? Because that's when the percentages settle down to not change by more than 1% on any simulation, on any 300,000 trials. Machine A loses 73% of the time. Machine B loses 86% of the time. Okay, here's the paradox. These two losing strategies, if instead of playing all machine A or all machine B, you flip a coin, a fair coin, and either play machine A or machine B on any step, suddenly you have a winning strategy. So both machines on average lose, but now you go up to 86% chance of winning if you randomly choose between these losers. This is sort of a little wacky. How could that be? Well, you got to dig in. If you look at if the amount of money you had in your pocket at any time was uniformly distributed, then machine B would actually lose with probability 0.47. So it looks like it's a winner. But if you just play it, it's not a winner. Well, what's going on? If you think about, you can be in one of 3 states. The remainder of how much cash in your pocket divided by 3 is either 0, 1, or 2. And you don't have uniform distribution over 300,000 trials. This is the distribution. For machine A, if you're just playing machine A, it is uniform because it's not referring to the amount of money in your pocket. But machine B, you're in state 0 a lot more often than you are in machine A, and you lose more there. And what's happening is if you've got a remainder of 2, your probability of winning goes up, so you jump up to a remainder of 0, but then you almost always lose. So you sort of cycle around in there, and eventually that adds up. So when you use the probability, when you calculate from the actual measured distribution, you get machine B is a loser and random choice is a winner. But it's not intuitive, but it's got a little tiny, less than 2 bits of structure make interactions between these 2 machines. So when you randomly use machine A, sometimes it randomly jumps you out of that loop between 0 and 2 more often. It's really hard to understand because it's not something that we can just describe about place, etc. So we don't have the intuitions nor the tools to talk about interacting processes linked by structure. Okay, I'm going to be very quick on this. Here's a gruesomely detailed example that I've come up with. If you randomly flip bits in a grid, sometime and stop when you get one of the 2 chessboards that you can get out of flipping bits, then people have argued, especially people who are arguing against evolution, you can't have structure come. So I started playing with this. Well, how does structure come? And I just look at a 4x4 board, and there's a dual problem of all black or all white squares. They're the 2 boards. And you measure the number of black squares B or white squares W, and the sequence of moves is you randomly flip one square at each step. Then it's a random walk on a symmetric random walk on the number of black squares over the range 0 to 16. Use that black box random walks, and you figure out that the analysis is easy. That if you start with a particular number of black squares, then the probability that you end up with all black squares is B over 16. So if you have 15 black squares, it's very likely to be all black. If you have only 3 black squares, it's more likely to end up be all white. The expected number of squares that are black remains constant with whatever you start with, doesn't change. And you can compute the expected time for how many times you have to flip a bit before you get to all white or all black. Okay, so then I started thinking, well, what if you introduce a little bit of geometric structure? So let's make this 4x4 board a torus. So every cell has 4 neighbors, rectilinear neighbors. And every cell has every square has 4 neighbors, so there's 64 possible pairs of neighbors, and you pick one of them, you look at its neighbor, and you flip it to be the same color as you are. And I thought, wow, that's going to add structure. You're going to get there more quickly. It turns out you don't. And then if I tweak this a little bit and say you have to choose a square so that you are going to change a neighbor, it looks like it's exactly the same as the up-down rule. The same analysis from it's a symmetric random walk, so it looks like it has the same behavior. But it doesn't. So we're going to talk about the up-down rule, which was the first one, and the single neighbor rule. From a statistical point of view, they look identical, but inside, the second one introduces structure. And with a little bit of geometric structure, can come from random events. Internal structure can come from random events. So let me just show this example quickly. If you think of one, where the black dot is, and that's the only black square and all the other squares are white, then the numbers listed, which have 0 on them, could change at the next step. So they have 0 protection. But the numbers with 1 on them, it takes at least 2 steps before they can change. So they're protected. And there's even one square which is protected for 3 steps. 3 steps have to happen before it's vulnerable to be changed. And each cell can have protection from all squares of the opposite color. And so here's some patterns of 3 black squares and how much protection they have. There's different examples. They're not all, but here's some different, current states and how much protection there is from turning black. So it's a sort of a convexity. There's a convexity measure there. And if you look at the equivalence classes of cells which are, or patterns which are transformable by translations around the torus and reflections, rotations, whatever, it turns out that there's, for 13 black cells, there's only 10 different fundamental arrangements. And here's what happens. And this just shows how many patterns there are of each size. Here's what happens. For B equals 14, there are 5 classes of cells. But if you go up to B equals 15, there's only 1 white square left. And the only way to come back to B equals 14 again, you can only come back with 2 white squares adjacent. So you start off, there can be arrangement of black squares, 14 black squares, where the white squares are not adjacent. But if you jump up 1 and come back 1, you've got a much more restricted class. And it's pretty complex to analyze this, but it turns out that there's a very complex sort of geometric structure emerging within the classes, which doesn't change the overall timing for the random walk, but which intermediate stages are represented is there. And then if you have another process, like machine A, which relies on the structure in some way, the 2 systems radically depart from each other. I'm not going to go through the details with some simulations, but the point here is that we are limited reasoners, and there's very simple systems which have hidden structure, which we don't see, and that hidden structure only comes into play when it's interacting with another system. And we don't have those tools to talk about that. I'm saying maybe it's not computation, maybe this sort of self-organization is something that's important because it's, at least in simulations, you can develop all sorts of complex systems out of the interplay of these hidden structures that come from having a little bit of geometry on them. In the Parondo's paradox, the geometry was only the remainder when you divide it by 3. It's not much, less than 2 bits, but it changes the outcome completely. So we may be missing, because we've become fixated on computation, we may be missing a whole bunch of stuff that's happening in natural systems. This is just an example of some. It's a question. So let's go at it. Who wants to defend computationalism? Yeah, there's a hand back there. And
Yeah, yeah.
Oh, all right. Yeah, thanks for this wonderful talk, really inspiring. I'm just wondering regarding your two examples of paradoxes that you discussed, that we have something missing. I'm wondering whether we're missing something or we're just not seeing what it's already out there. And I'm just giving an example because what you mentioned, I have the feeling that basically a lot of this paradoxes comes about that you assume that there are ergodic systems, so that the ensemble average, in a statistical sense, is the same as your temporal average if you do the dynamics. But it's, for a detecting system, it's very likely not. And in a sense, you could explain this because there's a history dependence of your dynamics.
yeah,
And you basically explains this. And there are developments where people start to question a lot of fundamental assumptions of ergodic theory for a lot of disciplines, including economics. And I'm just wondering whether that could be a way out to move beyond that.
yeah. I'm not saying there's no explanation. I'm saying we don't have convenient tools in the same way of some of the other tools. So I think there's more tools to be developed. And we shouldn't be surprised by that because science is always developing more of these tools and better ways to describe things. Ergodic theory is one of them, for instance. But you know, that geometric structure that's hidden is hard for us to reason about, and I don't see those tools being there at this point. But maybe you were saying the name of a tool and I missed it?
No, I'm just thinking like if it's non-ergodic, then if you have dynamics and space, then they're intertwined in ways that are non-intuitive for us if we think of basically ensemble averages.
Yeah, yeah.
And this is maybe the kind of a different view on the same what you said. Whether it's patterns, spatial patterns, or whether it's a dynamical system evolving time.
Yeah, and I'm looking. I want someone to invent some nice tools which are easy and intuitive. To talk about that, to capture the things, because in order to get the probabilities to work out for Parundo's paradox, the papers go on for tens and tens of pages to derive a set of probabilities that make it work, and it's just that one thing. There's no general tool that is useful.
Okay.
So I really enjoyed your talk very much, and so. What should a scientist be doing differently after your talk? I mean, I'm a neuroscientist, and computation enters in different forms. For example, you have the people who believe that the brain is Bayesian, and they have these kind of abstraction layers that think that you have certain computational principles that are instantiated in the brain. And other people will say, like myself, well, this is just kind of like a very, very vague abstraction, and the brain is doing something similar, but actually if you want to understand what it's doing, you have to understand the building blocks and how they interact with each other. Just ignoring all this talk about computation. Is that kind of what you're roughly after? And if so, what should we be doing differently in science if we ignore this layer? I mean, I personally believe that these abstraction layers are kind of, they can help us sometimes, but often they just lead us astray. Is what you're saying, understand the building blocks and how they interact?
Yeah. So for instance, that McCulloch Pitts paper, I think, led people astray and still leads AI people astray. So they can lead people astray. So I'm saying, hold on, think about your abstractions and whether you are so in love with your abstraction, you're going to ignore data that gets in the way of it. Well, yeah, but that happens over there. But let's talk about this ideal case, because then we can reason about it and talk about it. And I'm also saying that we're probably going to have to invent some new reasoning tools. We don't know what those are yet. So what I use this for is putting the brakes on saying that we're going to get computers to have artificial general intelligence anytime soon. I just think we're probably wrong about that. The evidence is not there from the way we do current neuroscience or current AI. That's what is needed. So I'm making an easy prediction because I don't think it will be gone against in my lifetime. So I'll die thinking I was right. But it's 300 years off before anyone figures it out. But what I'm hoping is that this might make some people think about stuff, and some kid somewhere in the world reads it and comes up with a brilliant way of talking about structure that no one has before. And it still takes 300 years for it to play out for neuroscience. But in the meantime, it's this new tool that we have that is useful for all sorts of complex systems, including economics, etc. So I don't have this is not a prescription, it's a question. Sorry? The next book, yeah. And thank you all for being my guinea pig on this talk today. I appreciate it.
Yes, thank you for the talk. Maybe a bit in line with John's question. Even if we can't say what the kind of tool that you're talking about would look like, can you think of anything worthwhile and useful that we would do with that tool without abstracting too much, ignoring too many details? Yeah, like if we do see and understand in the way that in the way that you said, yeah, what will we do with that?
Yeah, the best I can, my best guess is looking at interactions of systems which appear to be independent and the way they interact is, I think, a thing we don't do well. And, getting back to neuroscience, have you seen the paper, and I in one of my papers I talked about this many years ago, could you use the methods of neuroscience of single cell recording to understand a digital computer if you didn't know how the digital computer worked? And the paper came out 2 or 3 years ago where someone did that, and they had ablation studies. If you remove this transistor, Donkey Kong still runs on the machine. And it was sort of, it didn't come up with an explanation of how the computer worked. And so the tools you use are biased by how you think something works and what those abstractions are. And I'm just saying, be careful. I don't think anyone who's trying to start out their career could get away with giving a talk like this. I can get away with giving it just kind of an old guy who's been around forever, but I knew most of the people I'm talking about here that were still alive. And yeah. No, he wants to hold it.
Okay, great talk. I think I agree with what you said, yet I'm going to try and defend computation while also kind of throwing it under the bus.
Okay.
So you said that when people build scientific theories or when they iterate on scientific theories, they kind of identify a set of black boxes, right? These
they have black box tools.
Right. Okay.
The tools. Not the black boxes in the system, but the tools they use are black boxes.
To describe what's going on.
Yeah, to do some analysis, like the random walk theorem. You know the preconditions. You can just apply it. You don't have to rethink it for that case.
Okay. So you said that we need to identify better black boxes and not just use computation as the black box.
Right.
That we apply to everything. I would say that this is already happening, and I think most scientific fields are doing it, and these black boxes are just called computation.
Yeah, well, there's that where and that's, I think, dangerous in itself, because then people on the AI side think, oh, the brain is doing computation, so therefore computation is all we need to make artificial intelligent systems. But maybe that's not true, and there's a disservice done by relabeling whatever you see as computation, which was the criticism I had of the Churchill and Zanofsky book, that they relabeled stuff, because other disciplines have a real meaning and real theorems, and if you use the language, it's like McCulloch and Pitts saying neurons are AND gates and OR gates. They're not, and saying that they are doesn't help in a sense.
So what McCulloch and Pitts did was, when they cast neurons in terms of things that do computation, they took existing computational primitives and cast their behavior in terms of that. But then there's a new view of pan-computationalism, where a lot of processes can be termed computation. It's just like your black box idea, right? So morphological computation, for example, the idea that certain physical mechanisms perform a kind of computation that is useful for both describing systems and driving systems.
Yeah, and I think it's dangerous to call it computation, because then everyone else starts to think about it as Turing computability, which is a particular sort of thing. Which and there's a whole discipline of conferences of unconventional computing, where you do stuff that Turing machines just can't do without relying on quantum mechanics. I'm pleading for a little more subtlety and in the way words and things are used, and I'm not sure morphological computation is very helpful. Morphological processes which lead to something is helpful, but to call it computation, I don't think is helpful.
Okay, thanks. So would you say that perhaps instead of pan-computationalism, we should be doing pan-black-boxism?
The black boxes are all different tools, so no, it's not. I'm not using the black boxes inside, I'm using them outside. But I don't think any pan stuff is good.
Yeah, thank you very much for your very rich and interesting talk. And so actually there are non-computational approaches to cognition, right? Such as
Computational approaches to what, sorry?
Non-computational approaches to cognition.
Yes.
Such as the ones you mentioned, so poiesis, maybe enactivism. And so these approaches are still quite marginal, right? And they've always been rather marginal. And so according to you, how come they, why did they fail to actually become dominant?
Well, they may not be right enough, they may not be powerful enough, but it doesn't mean that, here's another thing with the brain that has happened in the last 30 years, not about computationalism, but about Alzheimer's disease. The mechanisms of Alzheimer's disease were chosen wrongly early on, and it starved out all other approaches to solving Alzheimer's disease. And it's only in the last 5 or so years that got broken through, and that old dogma said, oh, maybe that's not right. We got rid of the amyloid plaques, and they still, have Alzheimer's. So that wasn't the mechanism. But because of that dominance of that approach, at least in the US, now there's a whole set of reanalysis of NIH grants for Alzheimer's disease where people would just routinely turn down if they questioned that dogma, which now is, except for this one drug which just got approved by CDC, which maybe shouldn't have, and which is screwing up the whole healthcare economics in the US at the moment. Again, a problem from Alzheimer's misdiagnosis of how it worked. So, yeah, people, the natural thing in science is there's a herd mentality. This seems to be making progress, so this must be the ultimate answer. Those ones were too weak to win against computation, and computation had the advantage of Moore's law, just giving us more and more computation all the time. So we could get our AI programs to get better and better without having to think. We just waited for a more powerful machine and searched more and had more parameters. You see that in GPT-3 right now. So it's really hard to break out of these ways of thinking. And when the only alternatives are demonstrably weak, nothing's going to break out. It's going to take a long time for something new to come up. And I was just showing those 2 examples at the end because they're really simple, but they have buried dynamics. So there's an example there of something that you gloss over, even though it has consequential effects in those systems. But I agree, those old ones were quite weak and weren't strong enough.
Yeah, so I have 2 questions. Yeah, it's one question, but maybe you can
I'll give 2 answers.
tell something, some aspect of that. Okay, so there are 2 statements that were a little bit entangled for me, which is you said that is cognition really computational, and we need computation to understand cognition. And maybe, and then I would also like to know, do you mean also mathematics by computation in general, or, yeah, that's the question.
So I didn't quite get the question.
So the title of the talk is Cognition Computational?
Right.
And then at the end, at least, it sounded more like you say that do we really need computation to understand cognition?
I said we use it to understand it, and we will use computation as a tool. It's one of the tools we use, but it shouldn't maybe making it the primary metaphor is misleading us. Like I said, SpaceX uses a lot of computational simulation for their rockets, but that doesn't get the rocket into space itself. It's not the computation that does it. It's a tool. Although von Braun managed to get rockets into space without computation, but that was an earlier time. He didn't have it available.
So maybe I can ask a question. Would you distinguish between computation as a metaphor and what a computer does? And say that the first one is bad, but the second one is a useful tool? Because in the end, you used computation to show the paradox, right? To evaluate.
Oh, yeah. So it is a tool. And it was a simulation. I'm not saying throw out. I'm not in the world of June saying throw out computers. I'm saying don't look for more structure there.
Yeah, maybe related to some of the questions you gave and also Oliver's question right now. So I'm actually torn a little bit whether there's something really fundamental I don't really fully grasp, or that it's really about misunderstanding in interdisciplinary science. In the sense that you criticize neuroscience for using word computation for certain things to describe certain things as metaphors, although computation is well defined in the field of computer science and AI and has a long history, and you ask them to be more rigorous in terms how it's being used. But this happens all across sciences in interdisciplinary context. So, physicists get mad when you use universality in the wrong context. Biologists might get mad if you use adaptation or evolution in an incorrect context, or might be kind of thrown off. So I'm just, I'm not sure I really.
Well,
what do you mean exactly?
Yeah, I mean, the reason I talked very briefly about quantum mechanics and cosmology was because I think the metaphors have just gotten people, because they stick to those metaphors which get them confused and they can't see the reality. I mean, the physicists, the good quantum physicists can see the reality, but ordinary people get stuck in those metaphors and then get very confused by it. Instead of using some much more mathematical description, which is, proved to be accurate, through almost 100 years of quantum mechanics physics. So that was what I was trying to say there, that if you stick to a metaphor and push it too far, it can be useful, but if you push it too far, you can get yourself chasing things which are confusing. And we've seen that happen. That happens in science all the time over the last 2,000 years, all the time. So I'm just sort of trying to say why I'm not so sure about it being adequate for neuroscience, and I was using the fact that it all came from a very small group of people looking at a bunch of problems together, and then has become accepted. And part of it is because computation itself was so powerful. In my lifetime, the amount of computation that we can do has gone up on a single machine has gone up, and I've got a column coming out on this in IEEE Spectrum, by a factor of 10 to the 15th. That's a pretty big number in my lifetime. Since I first heard about computers to now, the amount of computation you have available to an individual without even using the cloud is a factor of 10 to the 15th. So it's been incredibly lucky, and I don't think we're going to see. My prediction going forward thousands of years is we're not going to see another event of exponential improvement in some physical process the way we saw it with computers, because there's a very precise thing about that enabled that, and that is that the information content of 0, 1 is independent of the mass of a number of atoms used to represent it, unless you get down to a handful of atoms, which is where we are now, where gates are down to about 7 atoms, and then you have to do things differently. By the way, computation as a metaphor is a metaphor we use to describe modern computers, because there is no longer a place where the number is. There used to be a place where the number is. And a modern Intel processor can actually have, which appears to be a serial machine, can have up to 180 instructions partially operating at once, which is what, and silicon designers have tried to keep that abstraction hidden from people, and sometimes they fail, which is why we see the Spectre path into getting data out of computers, because that abstraction fails in a couple of edge cases. So we even use computation as a metaphor for computers now, whereas they used to be aligned.
Biologist, I don't find this all that surprising, to be honest, because I think we always imagined as biologists that cognition and behavior and so on are really not completely reducible to computational processes necessarily, and certainly not without embodiment and complex spatial geometries. And so I would find it absolutely counterintuitive that we can create all these things with computational principles and do away with the complex bodies that animals have evolved, because then you would think, why did evolution ever go that path, creating these super complex bodies when we can have the full cognitive and computational power without any of this, So I think from our field, we kind of reach you the hand. I mean, we think this absolutely has to be this way, because otherwise it's unthinkable that you waste so much time and energy on building these complex bodies if it can all be done with a pure computational process in itself.
No, I agree, and that's why this organization, Sciences of Intelligence, is so good and strong, because there are people across the spectrum. In a sense, I'm arguing against mainstream technology sorts of driven people, where computationalists have infiltrated into neuroscience and other places, and you find it incomprehensible that anyone could have that view, but there's most places in the world where I would normally go giving this talk, even I would get really angry results. And it happened recently on Facebook. Someone posted something I'd said in a podcast, and very well-known computational people got really angry at me on Facebook. I woke up and I was just, you've got 27 mentions on, and I started clicking, and it was, he's an idiot. No, he shouldn't be saying this. This is so demeaning to me, some other person where I hadn't named anyone. So it does, this is why I gave the talk here, because I thought there'd be an appreciation and an understanding. It wasn't going to appear too radical, but in other places is really seen as radical. Yeah.
All right. So maybe to wrap up, a friend of mine always spoke about ideas as viruses that spread, and what a better time to speak about viruses than today. And I feel you questioned one of those viruses that has spread very widely. Yeah. I don't know if that is an antivirus that you're spreading, but I feel I'm going to question this metaphor of computation significantly for the next, maybe the rest of my life. So as far as I'm concerned, you infected me. And given the discussion, I think also some others might have been infected. Or
some view it as natural. Yeah.
So maybe we'll remember this event as the original ground zero of spreading the anti-computation metaphor virus.
Berlin is the Wuhan of...
Yeah, exactly. All right, thank you so much, Rod, for giving this beautiful and fascinating presentation. Thanks to all of you for being here and for asking great questions. Bye-bye.